So stationary points, how to find them and how to determine their nature. Hit pause, copy the lesson objective down. When you're ready, hit play and we'll move on. So we've got our function here, y equals x cubed minus 4x squared plus 5, cubic function as you can see, and we want to determine its stationary points. But at the stationary points, the gradient dy by dx is 0. So we've got 2 here. There's the first one, and there's our second one. So the gradient dy by dx is equal to 0 at these points. So in order to determine them, we differentiate our function and we set it equal to 0. It's a maximum point there, and it's a local minimum there. We say local because we keep it within that range, because functions sometimes have a tendency to do strange things, and there could be a second maxima which we're not looking at. So within the range we're looking at, it's a local maxima and local minima. Okay, you might want to hit pause, make some notes on that. Once you're ready, hit play. Now we'll move. Okay, let's have a look at this example then. Find the coordinates of the stationary points on the curve y equals x squared minus 4x plus 5. So as we say, at the stationary points, dy by dx is equal to 0. So we differentiate our function in the first instance. So we've got y is equal to x squared minus 4x plus 5. Differentiating that, dy by dx is equal to 2x minus 4. So we'll state at the stationary point dy by dx is equal to 0. Therefore 2x minus 4 is equal to 0. So we can say 2x equals 0. Whoops, not equals 0. 2x equals 4 because we're adding 4 to both sides. Let's get rid of that. Back to red. So 2x equals 4, adding 4 to both sides and dividing by 2, x is going to be equal to 4 over 2, or 2. So that's our x coordinate. How do I find my y coordinate? It's a question mark. Well, to find a y coordinate, you sub for x back in the original equation. Find y. Just going to change that to blue. So we've got y is equal to x squared minus 4x plus 5 at x equals 2, y is equal to 2 squared minus 4 times 2 plus 5, which is equal to 4 minus 8 plus 5, which is equal to 1. So coordinates of the stationary points are point is 2, 1. Okay, so hit pause, copy the example down. When you're ready, hit play and we'll look at another example. Okay, so in this example, it says find the coordinates of the stationary points on the curve y equals x cubed minus 3x squared minus 9x plus 7. So we've got a cubic, so technique is exactly the same, maybe a slightly more involved. Y equals x cubed minus 3x squared minus 9x plus 7. So we differentiate dy by dx, which gives us 3x squared, squared minus 6x minus 9. So at the stationary point, dy by dx is equal to 0. So we set 3x, therefore 3x squared minus 6x minus 9 is equal to 0. Straight away I can see that I can divide by 3, so I'm going to do that, which leaves me with x squared minus 2x minus 3, which is equal to 0. I now need to factorize and solve. X squared makes it nice and simple. So it's x times x. I've got a minus 3 there. I'm just going to work on it over here. Minus 3. Factors are 1 and 3. One of them's got to be negative to give me a minus 2 there, so it's got to be the minus 3. So it'll be x minus 3, x plus 1. Therefore, either x minus 3 is equal to 0 or x plus 1 equals 0, which implies that x is equal to 3 or x is equal to minus 1. Now I need to find the y coordinates. Let's just draw a line here. Switch to blue. So, when x is equal to 3, y is going to be equal to 3 cubed minus 3 times 3 squared minus 9 times 3 plus 7. So we've got 27, interesting, minus 27, which is quite nice, minus 27 plus 7, which leaves me with 20. So our coordinates then are going to be 3, 20, and just go change one more time. It's like, let's see, let's go with black. And you say when x is equal to minus 1, y is equal to minus 1 cubed, minus 3 times minus 1 squared, minus 9 times minus 1 plus 7. So we have minus 1 minus 3 plus 9 plus 7. Just checking, negative. That's going to be negative as well. Okay, so we got minus 4 plus 16 equals 12. So our coordinates, this instance, are minus 1 and 12. So our stationary points are at 3, 20 and minus 1, 12. Okay, so we've got two stationary points. Solved quadratic. We solved the quadratic derivative to get our two x's, and then we put it back in the original equation to find y. Hit pause. Copy the example down. When you're ready, hit play again. Okay, just wanted to make sure that hopefully someone spotted that should be a negative there. Minus 27 plus 7 should be minus 20. So that's minus 20 and minus 20. Great. I've got two questions for you to attempt. So once you've made that adjustment, we'll move on. Okay, so two questions for you to attempt, question 1 and question 2. Hit pause, have a go. When you're ready, hit play, and we'll look at the stationary points. Okay, so you should have 3 and 6 on question 1. On question 2, you've got two stationary points. 0 and 7, and that might have been a bit awkward. 8 over 3 and minus 2 and 13 over 27. Okay, So now we can determine whether we've got a maxima or a minima point. We can determine that where the gradient is 0. It's going to be a maxima, minima, or what's called a point of inflection. But we haven't been able to determine yet which type it is. Is it maximum? Is it minima? Is it a point of inflection? So we can use the gradients to determine that. First instance, if we look at the sign of the gradient, what's happening from P1 to P2? The gradient on P1 is positive, and it switches to a negative. So it's just very close to the where the gradient is 0. It's switched from positive to negative. And on a minima point, the gradient is changing from negative to positive. So this is a little aid memoir, something to help us remember. At a maximum point, the gradient is changing from positive to negative, and the minimum point is changing from negative to positive. So hit pause, make a sketch, make some notes. When you're ready, hit play again. The third point where the gradient is 0 is what's known as a point of inflection. So we have these points here where the graph changes, but the gradient stays similar to what it was before. So here we've got our positive gradient, then it changes to 0, but just after the stationary point it's still positive. And the same thing here, we've got a negative gradient, then our stationary point, and then it remains negative. So these are points of inflection. You can remember them as such. The gradient stays positive, and the gradient stays negative. Again, hit pause, make some notes. When you're ready, hit play again. And let's have a look at this example then. Right, well, we've got to find the coordinates of the stationary points in the first instance, and then we've got to decide its nature. Is it maxima or a minima? Well, first we've got to differentiate it. We've got, we've got y is equal to x squared minus 4x plus 5. We differentiate that, we get 2x minus 4. So at the stationary point, dy by dx is equal to 0. So we got 2x minus 4 equals 0. It's very similar, which means that x is going to be equal to 2. And we've got to find y by subbing for x in the original equation. I think this is the same question as earlier. So y is going to be equal to 2 squared minus 4 times 2 plus 5, which is 4 minus 8 plus 5, which is 1. So our coordinates is at 2, 1. Okay. Right. So is it a local maxima or a minima? Well, we check what's happening to our gradient just before and just after. So dy by dx is equal to 2x minus 4. So just before 2, if we try 1, at x equals 1, what's happening to the gradient? The gradient is equal to 2 times 2 minus 4. Sorry, at x equals 1. Change that to a 1. 2 times 1. So it'd be 2 minus 4, which is minus 2. So it's negative. And then we check at x equals slightly more than 2 at 3. And dy by dx is equal to 2 times 3 minus 4, 6 minus 4, which is 2. So the gradient has gone from negative to positive. So we've got a local minimum. Okay, so hit pause, make some notes. When you're ready, hit play again. Okay, so let's have a look at this question here. Find the coordinates of the stationary points first, and then we've got to decide whether it's a local maxima or a local minima. Well, we've got y is equal to x cubed plus 3x squared minus 3. Differentiating that gives us 3x squared plus 6x. So at the stationary points, dy by dx is equal to 0 at the stationary points. So what we do is we equate then 3x squared plus 6x equals 0, and divide by 3, which leaves us with x squared plus 2x equals 0. Factorizing, x times x plus 2 equals 0. So either x is equal to 0 or x equals minus 2. So now we've got to determine y. Just switch color. Let's go back to red. If x is equal to 0, y is going to be equal to 0 plus 0, so minus 3. So we've got a set of coordinates there, 0, minus 3. And if x is equal to minus 2, y is equal to minus 2 cubed plus 3 times minus 2 squared minus 3. So that's minus 8 plus 12 minus 3. So that gives us 12 minus 11, which is 1. So our other coordinates then are going to be 1 and minus 2. Okay, so now we've got to determine whether they're local maxima or local minima. Okay, wrong way around. Switch that. Minus 2, 1. So we've got to determine whether they're local maxima or local minima. So if we look at the 0, 3. So we look at just before. So if x is equal to minus 1, what happens to the derivative? dy by dx is equal to 3x squared plus 6x. So it'll be 3 times minus 1 squared plus 6 times minus 1, which is equal to 3 minus 6 minus 3. And just after 0, so if x is equal to 1, dy by dx is going to be equal to 3 times 1 squared plus 6 times 1, which is equal to 3 plus 6, which is equal to 9. So we've gone from negative to positive, so it's a local minimum. And if we transition then, and we look at the other point, at minus 2, 1, what's happening there? Well, just before minus 2, so if we look at if x equals minus 3, we got dy by dx is equal to 3 times minus 3 squared plus 6 times minus 3, which is 27 minus 18, which is 9, so positive. and just after minus 2, we've already done that, minus 1. So if x equals minus 1, then dy by dx is equal to minus 3, which is negative. So going from positive to negative, which is a local maximum. Okay, so hit pause, make some notes on this question, and once you're done that, we'll move on again. So we've also got a second method of determining whether we've got a maxima or a minima, and that's by using the second derivative. Here we've got this graph y equals x cubed minus 3x squared plus 8, sketched there, and then we've got a second graph. That graph is of its derivative, 3x squared minus 6. So if we look, consider the local maximum first. The second derivative, and the local minima as well, the second derivative at the maxima is going to be negative, and the second derivative at the local minima is positive. So if we test the second derivatives, we can find out whether we've got a local maxima or a minima. Unfortunately, it doesn't help us to find the point of inflection. Okay, so hit pause, make some notes there. So if you've got the second derivative less than 0, you've got a maxima. If the second derivative is greater than 0, you've got a minimum. Okay, so for this question, example question 6, we need to find the coordinates of the stationary points for this curve and decide whether they're local maxima or local minima. Well, first we've got to differentiate. Y equals x cubed plus 3x squared minus 1, and if we differentiate that, we get 3x squared plus 6x. Now, at the stationary point, dy by dx equals 0. So we got 3x squared plus 6x is equal to 0. We can divide by 3. It leaves us with x squared plus 2x equals 0. I can factorize that. So that implies then that either x is equal to 0 or x equals minus 2. So we can now find y. At x equals 0, y is going to be equal to 0 plus 0 minus 1, so minus 1, which gives us 0 minus 1. And at x equals minus 2, y is going to be equal to minus 2 cubed plus 3 times minus 2 squared minus 1, which is minus 8 plus 12 minus 1, which is 12 minus 9, which is 3. So we've got coordinates here of minus 2 and 3. Now then, we want to determine whether we've got a local maxima or local minima. So we say at x equals 0, d2y over dx squared, if we differentiate our gradient, we get 6x plus 6. So d2y over dx squared is going to be equal to 6, which is greater than 0. So this is a local minima. And we say at x equals minus 2, d2y over dx squared is going to be equal to, if we sub in here, we've got 6 times minus 2 plus 6, so it's minus 12 plus 6, it's negative, so it's going to be a local maxima. Okay, so hit pause, make some notes, and I've got some questions for you to attempt. Okay, so you got exercise 12L there. It's just the 7 questions. Good luck.